So far we have discussed two types of biasing a transistor at a desired current. In one case we sense the difference between desired and actual currents at the drain terminal and feedback to the gate. In the other case we sense the difference at the source terminal and feedback to the source. There are two more varieties that are possible. One of them is to sense at the drain and feedback to the source terminal. So let's say we have the transistor, and because we are feeding back to the source terminal, we keep the gate at a fixed voltage VG0. Now we want to sense the current difference at the drain. So we have ID. So to be able to sense the current difference, we connect a current source I0. Okay, this gets connected to the supply, some voltage, and now I'll come back to what happens to the drain node, but this is the source voltage Vs. Okay, so if ID is more than I0, that is the actual drain current is more than the desired current, then we must reduce VGS. If we reduce VGS, then the drain current will come down. Now VGS equals VG0 minus Vs. So this means that to reduce VGS, we must increase Vs. Okay, and similarly, if ID is too small, if ID is smaller than I0, then we must increase the drain current, and we do that by reducing the value of Vs. Okay. So this is the action that we want at the source. Now what really happens at the drain? The difference between I0 and ID flows into this capacitor Cp, which consists of the parasitic capacitance at this node. Now if ID is too large, that is ID is larger than I0, then this current will be negative. Current will be drawn out of the top plate of this capacitor. So if ID is more than I0, then the drain voltage Vd reduces. Okay, and the opposite happens if ID is less than I0, then the drain voltage would increase. Now you see that Vd reducing is an indication that the drain current is larger than what is required, and in that case we must actually increase Vs. Okay, so the sense of change we want at the source is opposite of what's happening at the drain. So if Vd reduces, we must increase Vs, and if Vd increases, we must reduce Vs. Okay. If Vd reduces, this means that ID is greater than I0, and this means that Vs must increase, and similarly if Vd increases, this means that ID is smaller than I0, and this must decrease. Okay. So how do we accomplish this? What we really need is some block which takes its input, which is the drain voltage, and gives an output which is the source voltage, and also it must have this behavior, that is if Vd reduces, Vs must increase, and so on. So let's say these are the input and output terminals of this block, whatever that is. Then the output versus input, that is the voltage at the output versus voltage at the input, should have a characteristic like this. Okay, which means if this Vin increases, Vout, what is driven to the source, should actually decrease. In other words, it must have a negative incremental gain. Okay, so you must drive the source using an amplifier or some block which is driven by the drain voltage, and this must have a negative incremental gain, so that the sense of variation is as shown here. Okay, so this is slightly more complicated than our original case. The very first case we discussed, we sensed at the drain and fed back to the gate. The sense of variation we wanted at the gate was exactly the kind of variation we were getting at the drain. So, we could connect it with a positive incremental gain in general, and even a direct connection was okay. Whereas in this case, a direct connection will certainly not work, and you do need a negative incremental gain between the drain and the source. Okay. So, because this is slightly more complicated, we normally would not use this for a simple common source amplifier, but these structures do occur in many places in circuits. I will show you one example of how to accomplish this. This is at VG0, some bias voltage at the gate, and this is I0. Like I said, I should take this, make it go through a negative incremental gain and drive the source. There are many options possible, but I will use one particular option using an op amp, and I assume that you are familiar with the concept of the ideal op amp. Okay. If not, please go through the relevant lecture material from basic electrical circuits. The ideal op amp, I will describe it very briefly here. It has an input VD between two terminals. It has two input terminals, and the difference voltage is called VD. Okay, the input terminals are marked with plus and minus, and this is the difference voltage, and then output voltage VO. Now, what it means is, if the op amp is arranged to be in negative feedback, what does that mean? There is some circuitry around the op amp. You can't use the op amp just by itself without anything else. So there is some circuitry around the op amp. Okay, VO gets connected to that, and the input terminals of the op amp also get connected to that. What is the meaning of negative feedback? It means that the action of this circuit, whatever is the rest of the circuit, is such that VD reduces if V0 increases. Okay. In other words, this stuff has a negative incremental gain. Okay, it doesn't have to be actually a gain. All it has to do is to make sure that VD, which is the output of this block, as far as this block is concerned, you can think of this as the output and this as the input, and this block should be such that its output reduces if the input increases. That is, this VD must reduce as V0 increases through the feedback circuit. If that's the case, then in case of an ideal op amp, VD goes to 0. Okay, that is, the difference between these two terminals will be forced to 0 by the op amp. Okay, and this concept of VD being forced to 0, this is known as the virtual short. Okay. Now, if two nodes are shorted to each other, obviously they will be at the same voltage. In the case of an op amp operating in negative feedback, these two terminals are not shorted together. There is no wire connecting them. But this op amp and the negative feedback together will force these two voltages to be exactly the same, and that is what the ideal op amp does. Okay. In case of a real op amp, VD will become very small, but not exactly 0. In case of an ideal op amp, it becomes 0. Okay. These things are described in more detail in basic electrical circuits, or you can use some of the textbooks that you may have which describe the op amp. So, I am going to use this block to complete the feedback. What I did was, I took the drain voltage, fed it to one of the inputs of the op amp, and drive the source with the output of the op amp. Okay, and this other input of the op amp, I call it VD0. Basically, it's some fixed bias voltage as far as I am concerned right now. This is VD0. Now, how should the circuit be configured? Obviously, first of all, we already know that the incremental gain from the drain to the source must be negative. So this appears to be the negative terminal. Okay, so that's what it should be. The terminal on the left side is the negative terminal. You can also examine it from the viewpoint of the op amp and you will reach exactly the same conclusion. Okay. So what must happen is that if Vd increases, Vs must reduce. So that tells you that the sense of the op amp must be like that. Now, going by what I described to you just about the op amp, okay, the difference voltage in this polarity is Vd0 minus Vd, okay, and I will now analyze the rest of the circuit, that is from this point onwards. This is the output of the op amp that I call Vs. Now what happens if Vs increases? This ID here will actually reduce because the gate source voltage reduces, and in that case I0 minus ID will flow into this capacitor and raise the drain voltage. The drain voltage increases, and the difference voltage of the op amp, if the signs of the op amp were like that, the difference voltage of the op amp is Vd0 minus Vd, and this will fall down. Okay. So it is in the correct sense for negative feedback. The way you evaluate the op amp signs for negative feedback is you assume some set of signs and then you work around and then see if this difference voltage reduces as V0 increases. Okay. So if I choose the signs to be like that, okay, then as Vs increases, ID will fall down, which will make the drain voltage increase, which will make the difference voltage Vd, this Vd here, decrease. So it is in negative feedback. So the correct signs of the op amp are like that. Okay. So this is the way of biasing a transistor at a constant current I0 by sensing at the drain and feeding back to the source. Okay.